Welcome to the second video for our beam deflection lab. In this one, I'll talk about how you should be setting up the values for your theoretical deflection and rotation equations and the boundary conditions you should be using. We're looking for the deflection and rotation equations for this beam right here. So let's get through on that. Obviously, when we're doing this, we want to maintain sort of as a variable a, that's that distance from this point to this first deflection, and also, or not first deflection, first load, and then also there's this from this load to this reaction. I, you can leave that as a variable. The Young's modulus, please leave that as a variable. And P, the load, leave that as a variable. Oh, and the total length, of course. Please leave that as a variable. So when we're doing this, obviously there's three sections that we need to be cognizant of. When we're doing that, obviously we need to integrate quite a bit. And so that's I'm not going to run through all of it for you. You have to do that. But let's look at our boundary conditions. So our boundary conditions are going to be, and actually, now, let's start with an assumption we can make that's pretty bold and useful, not just in this case, but in many other cases. And that is a symmetry boundary condition. This is symmetric about the load, right there. So we don't actually have to worry about both halves, right? We can just worry about one of those halves. So if we draw it up like this, we've got, I guess I'll use all sorts of fun colors. We've got our reaction right there. We've got our applied load right here. And we have some internal loads right here. In this case, of course, this load and this load are two forces are going to be zero. We'll only have a moment, so that's zero, that's zero. So we don't need to worry about that. We do know, so if we do this, we can use a boundary condition of symmetry. And what that means is that when we look at this, we say, okay, sure. Right away we can go ahead and say that the deflection at point 0, or at the beginning, at this point right here where there's a pin, that's got to be 0, right? There's a pin, it's holding it up, got to be 0. At this point right here, we do not know what the deflection is, right, at L over 2. There is going to be some deflection, we don't know what it is. What we do know is that the rotation at L over 2 is 0, right? Because it's symmetric, so that rotation has to be 0. And so we've got both of those that we can work with. And then I guess you can by a symmetry, you can say that the deflection at L over 2 is equal to the deflection of L over 2 if you really want to do that for the rest of it, but you don't actually need that to solve the problem, because you'll have a constant of integration resulting from integrating from the moment, which you have the moment equation, to get to the rotation, and you won't be able to solve that right away because you don't know the rotation in any given. And you'll be able to solve for that because of this, and then you'll have another constant of integration owing to your integrating again to get to your deflection equation, but that'll be taken care of by this. So you only need these two to get all of your equations done. Now you're also going to have the fact that at this point right here, you're going to have a change in the functions. So you're also going to have to consider that the deflection at A is equal to the deflection at A. So from beginning, and then this is from A, because there's a continuity of deflection, and there's also going to be the rotation at A is equal to the rotation at A. You're going to have to worry about that as well, but you're not going to need to solve out for there being no deflection at this point right here. You can say there's no rotation at this point right here, and that generally that symmetry trick is actually very, very useful in a lot of situations. I've used that to save quite a bit of computation time in things that I've done. So keep that in mind, because that'll be the difference between sometimes waiting a couple days for some sort of nonlinear analysis to run to waiting a few hours later in your lives. So assuming that computation time doesn't get so cheap and easy that it doesn't matter. So that's what you'll use for determining your theoretical rotations and deflections. So please use these to determine the theoretical deflections and rotations as a function of your unknown Young's modulus.